Okay. Let's begin.
Well, this one got this guy. This one got this guy.
So today's going to be another one of those kind of theory classes. I think it's pretty much the last one we're going to have. But I wanted to explain the connections that I've been alluding to this whole time. So we are now going to talk about, I believe it's 3.4, kind of matching that with 4.4, where we're going to talk about how we would evaluate definite integrals. And we'll talk about the FTC, otherwise known as the Fundamental Theorem of Calculus. So, last time, we saw the following. We have something that we call the definite integral. It has that symbol, fx dx, and it was defined by an infinite Riemann sum. That is a sum whose purpose is to add up the areas of rectangles under a curve, set up somehow under a curve, and we call this the definite integral. Other than that, maybe some other phrases that you'd want to know. This notation, as I said, comes from Leibniz. It's been called the integral sign. The A and the B in this case, these are called the limits of the integral. Where A is called the lower limit, and B is called the upper limit, respectively. The dx is called the differential. You've seen that guy before. They have meaning in and of themselves, but in this case you can just think of it as something indicating who the independent variable is. And lastly but not least, the f of x itself in this context is called the integrand. And this guy is the definite integral. It finds the area under, I'll explain why I'm putting under in quotations in the next class, under f on the integral dd. So last time we looked at all that. Now I want to know, want to show you guys how we're actually going to be computing these. Okay? So you want to find the area under a curve. How would you actually go about computing it? Well, we have the definition right here. We'll compute it like that. So let's actually do an example where we're going to compute a definite integral. So an example is, find the exact area. Now once I say exact, it means I'm not talking about doing a finite left-hand approximation or right-hand or midpoint or some finite Riemann sum. I mean find the exact area. No gaps, no overestimation, no underestimations. Find the area. Find the exact area under, suppose actually the function x squared on the interval 0, 1. One thing you can appreciate is what I'm saying. In other words, I would like you to compute this expression. That's another way of saying exactly the same thing. You can just say, find this. It's the same as me asking you this. we go about doing that? Well, of course, we have to find the pieces to plug into the formula. So finding our delta x would be nice. Delta x would always be minus a over n. Here, remember a and b are the left and right endpoints of the integral respectively. It's going to be 1 minus 0 over n, so that's going to be 1 over n. We also saw last time that the x sub I is always going to be a plus I delta x. This means our a is 0 and our delta x is 1 over n, so this will result in I over n. I will then have to find my function evaluated at the xi. My function here is x squared, so I'm just going to take the square of this expression. Therefore, this guy is going to be equal to the limit as n approaches infinity of the sum, either from 1 up to n, of f of xi times delta x. And so now we'll go about computing that. We've actually computed a guy like this before. In fact, if you look back at your notes, I think this is exactly the guy that we computed before, where I said, oh, by the way, we're going to look back at this example of a couple of classes from now. You'll see. And yeah, this is it. This was the guy I actually computed before. Let's actually run through it again. Here's the summation. I is the variable. We have a property of summation that says we can factor constants out. Anything that's not an I is a constant with respect to this sigma. So, therefore, I can factor out the n's, for example. I'll get 1 over n cubed if I move those out, because there's an n squared here and an n. And I would be left over with I squared. Now, this expression, we have a formula for it. That is n times n plus 1 times 2n plus 1 all over 6. Remember, all those formulas we need to have memorized. So it ends up being that to find this area, I need to compute this limit of a Riemann sum. And that's pretty much going to be the limit as n is approaching infinity. Because I'm taking an infinite limit, I know that only the highest powers actually matter. So if I look on the top, what I would have is I would have a 2n cubed plus a bunch of things I don't care about. And on the bottom, I would have 6n cubed. Goes to the ratio of leading coefficients, you get 1/3. Turns out the area under the graph x squared on the interval 0, 1 is 1/3 squared units. So if you were to find this guy, the area of the shaded region, the answer is 1/3 whatever units squared. Now everything might seem hunky-dory at this point, but it doesn't, you don't need to go far to kind of realize that there are some significant drawbacks to this method. So, I'm not going to fully work this one out, I just want to show you how things can become an issue. Suppose I wanted to compute, say, 1 up to 5 of x cubed plus x squared plus 1. This function itself, not super complicated, but let's say I actually wanted to do that. Again, in the grand scheme of things, this is a very simple function. However, by our definition, by Rousseau's definition, I need to know what to plug in here. So let's start from scratch. We find delta x. B minus a over n, it's going to be 4 over n. Our xi is going to be a plus I delta x. That's going to be 1 plus 4i over n. And of course our f of xi is going to be, I need to plug in this expression into that guy. So I'm going to have 1 plus 4i over n cubed plus 1 plus 4i over n squared plus 1. And so now, to plug this into that guy, this guy's I would be equal to, well, the limit as n approaches infinity of the summation I goes from 1 to n of f of xi times r delta x. And now to compute this, I'm going to have to find the cube of this expression, the square of that expression. I'm going to have to recombine terms, apply formulas, right? Ultimately, I'm going to want to isolate the summation of I cubed and the summation of I squared. But you can kind of see, just with a little flick of a pen, if I put a 4 here, then none of the formulas that we have work anymore. You'd have to figure out what does it mean to add this first, the first n where you're taking the 4th powers, right? Or if I had a square root here, what does it mean to add the first n square roots? Like, the formulas can get really tedious, really complicated. And at this point, very quickly, with a very simple function, this gets kind of annoying. Quickly. You don't need a very complicated function for you to not have a good time doing these anymore, right? So now you kind of ended up in a situation where you're no better than that guy who's sitting around counting rectangles and adding up areas, right? It's going to be very computationally intensive to do that. So now I might ask, is there a better way? And of course the answer is yes. What is the better way? Well, there was one situation in which we saw a shortcut. It's that same motivating example that we keep going back to. That distance velocity graph, right? We pretended that, you know, we had this guy, and then we plotted the velocity. So here we were plotting distance, here we were plotting velocity, and that was constant. And we found that the area here, we saw this, the area under v of t on the interval 0, 3 was actually equal to the position function evaluated at 3 minus the position function evaluated at 0. Where specifically the position function was the antiderivative of v evaluated at the endpoints. In other words, this was basically saying if we found the area under the velocity graph, technically you should have absolute values here, but we'll talk about that. We don't have to worry about that because the function is positive here. The result is going to be its antiderivative evaluated at the endpoints. Now, if this were true in general, that would be great because this is going to be a heck of a lot easier than computing something like that. Right? Especially if I have a nice function that we know the antiderivative for, that would be pretty nice, be pretty simple by comparison. And so the question is, okay, we saw that this worked out here. Does it always work out? The answer is yes. Turns out you can actually say this in general. The area under any function on an interval can be described as the difference between the difference of its antiderivative at the endpoints of that interval. Very strange thing to realize is true, but it is actually true. So, turns out this is true in general. In fact, we have a name for this statement. It's called the evaluation theorem. Some people, out of respect for our forefathers, call it the Newton-Leibniz formula. But basically it says that f of x be continuous on a b, and big F of x be any antiderivative of f, turns out, in general, you will be able to find the area under F by taking big F evaluated at the upper limit minus big F evaluated at the lower limit. This will be a true statement in general under these conditions. Now again, this is the motivating example. That's what made us think about it. You know, this is even kind of the kind of idea that caused Newton to think about it. I mean, what Newton was concerned with was, you know, tracking the planets moving through our solar system. So he had to know where they were, how fast they were moving in their orbits. So distance and speed became obvious things that he was very concerned about, and you know, he started to notice little things like this. And so there seems to be some connection between the two here, between a derivative and an antiderivative and an area. So let's actually see how we can actually show that this is the same. I'm going to start with you can start with either side, but I think it's easier to digest if I start with the right side. Now you want to be able to describe this guy as that guy. First thing you're going to realize, of course, is what this guy means is he's the limit of a sum. Okay? So already on this side you see some key differences between that side. First of all, this side has a bunch of xi's, whereas that side doesn't. So the first thing that you probably want to do to try to make that side look like this side is let's get all these x values in there. We can immediately have 2 because we know that b we normally call xn, and we know that the a we normally call x0. How do you get the other guys in there? Well, we do what we always do as mathematicians, very sneaky, add 0 in a very convenient way. So what I'm going to do to get all the other xi's in, let's add and subtract them. Down here, going all the way down to the end, you'd have something like f of say x2, x1 plus f of x1 minus f of x0. Right? So you add them in. You add in all the other guys. That seems to make it more complicated. Well, not so quick. Look at each pair. This guy will go with that guy. And this guy goes that guy. This guy goes that guy. Here I have some function evaluated at the endpoints. You might think, where have I seen such a difference before? Well, I'll tell you where, since it probably won't be so obvious at the moment. It's from the mean value theorem. It's somewhere where I would have seen such a difference. What would the mean value theorem say? Well, we know the mean value theorem, let me just quickly remind you here, f is continuous on an interval AB, then there exists some c in AB such that if I take the derivative at that point c, it will be f of b minus f of a over b minus a. In other words, another way we wrote this down, at least the first time we looked at it, was this. We could look at the difference of f values on an interval as the derivative evaluated at some point in that interval times the length of that interval. Right? So this means I can think of this difference as this guy, and we already even have notation for this. This is what we call delta x. So it turns out I can see all of these guys, and I can actually replace them . It's actually not going to matter too much anymore. I can replace them all with those guys. Now, I notice here I have big F. I'm applying the mean value theorem to big F, which means in order to be able to do this, in order for this to be legal, I would need to know that big F is actually a continuous function. How do you know that big F is a continuous function? How do you know this is legal for me to do? That's a question for you guys. Any ideas of why big F is a continuous function? Yeah.
So you can take the derivative because big F is there.
Because you can take the derivative. We saw many moons ago that differentiability implies continuity. If something is differentiable, it's automatically continuous. It's not true the other way, but it's true in that direction. Differentiability implies continuity, and big F is differentiable by definition. It's the antiderivative of something, which means its derivative has to exist, and in fact, we know it's that guy, right? So big F is differentiable, therefore it's continuous, therefore the mean value theorem will apply to big F. Therefore, I can replace expressions like this with expressions like that, which a shorthand for such an expression, well, in fact, let's actually write this down a little nicer first. Big F prime, by definition, is going to be little f. And of course, there's a shorthand way for writing this, right? That's just like writing a summation. I goes from 1 up to n of f of ci up to x. Doesn't that guy look familiar? This is actually a Riemann sum on this side. So what we've seen so far is that f of b minus f of a is equal to, it turns out, a Riemann sum, surprisingly enough. Now what we can do to make it a real integral, a definite integral, I just take the limit of both sides. And of course, the right side will give me the definite integral of f. While on the left side, there are no n's here. That just stays the same. And we have, this is true. This is true in general. So this is called the evaluation theorem. And I know it didn't take a while for us to go through this, but really, we are covering centuries of mathematical development here. I mean, if I went through that proof and you're like, I don't get it, it's okay, really. Like it took people literally decades and centuries to get it, right? Okay, so, but now that we know in hindsight, we can look back and it's like, oh, no, obviously. Well, isn't that obvious? Yeah, no. That's kind of like the same thing that happens when in class I'm doing examples and everyone's like, yeah, I totally get this. And then they go on tests and they bomb it because they think they get it, but they don't. Because to get through it yourself is very different than looking in hindsight at someone else already solving the problem. Anyway. That's an important statement, and it is true in general. And it is actually a part of the FTC. Here's another interesting fact. Remember that area function I described to talk about, where I was introducing the idea that area has something to do with derivative? This was like 2 classes ago, the big A of x. Let's actually look at that function a little bit more. Suppose I had some function that is defined in this way. It is the area from A up to x underneath this other function. So I have a function that's defined as the area under something, right? A function that's defined as an integral. Okay. Now, we're also going to assume that this thing can somehow be computed. We might not even know the answer, but we're going to assume that there is some answer here. Assume that big G of x is an antiderivative. And so now here's the question. What is f prime in this case. What is the derivative of an integral? Is the question. Huh?
So where does g of x come from?
I'm just assuming this is some antiderivative of f. Right. We're under the assumption that we can find an antiderivative. Okay. It's not always possible, it's not always easy, but if we have it, we know certain things have to be true. Now, by the evaluation theorem, this guy is actually equal to big G evaluated at x minus big G evaluated at a. In other words, my big F is going to be big G evaluated at x minus big G evaluated at a. This means if I'm to take the derivative of both sides, I would get the derivative of this guy plus 0, because G of a is a constant. But G of x is an antiderivative, which means G prime is actually just a little f. So in other words, the big F prime is just going to be small f. So I can summarize that fact by saying the following. In other words, if I take the derivative of an integral, I just get the original function back. Differentiating an integral, these guys just kill each other and you get the original guy. Kind of like an inverse function, an inverse operation. So this is one of the statements that makes people say things like, the derivative and the integral, they're two sides of the same coin. They're like inverse operations of each other. They're not exactly inverse operations because, of course, a derivative can reverse an integral, but an integral can't fully reverse a derivative. There's always going to be that plus c that you're not sure what it is. But derivatives reverse integrals, and integrals almost reverse derivatives, so they're kind of like inverse functions with one little glaring hole. But this is true. Differentiate an integral, you get the original function back. Now these two thoughts, we can summarize them in, they're normally summarized in one theorem. Now I know we went through this in a few minutes, but as I said, it took a lot of mathematical development, a lot of mathematical thought to get to these two statements, and ultimately they form what we call the Fundamental Theorem of Calculus. This is it. This is why we're all here. This is why this class exists. This is why calculus, as it is studied in the modern age, is what it is, because of this theorem. The theorem says if f of x is continuous, and we know what that means. Limit as x approaches a is f of a on an interval ab, and suppose we can discover an antiderivative of this function. Then we know two very important facts. One, right, sometimes referred to as part one. Then part one of the things we know is that the area under f is given by its antiderivative evaluated at the endpoints. It's called part one of the Fundamental Theorem of Calculus. Second thing we know, sometimes referred to as part two, or the second Fundamental Theorem of Calculus, is that the derivative of an integral is the original function. Seems like a very doesn't even seem as important as a lot of the other theorems that we've looked at, but it is super important. For many reasons. One of the reasons is it connects two different fields of mathematics that for a long time no one knew were connected. Finding areas and finding rates of change. How is an area related to a rate of change? Turns out this is how it's related. So you have two very different schools of thought. You had people over here measuring how fast things change. You have people over here counting rectangles. Turns out they were kind of doing the same thing. They were solving the same problem from different ends. And this is where they meet in the middle. This is the fundamental theorem of calculus. And it shows a lot of how math research even happens today. You know, there are no really pockets anymore of like, oh, there's a bunch of math for this thing, and there's a bunch of math for this thing. No, everything is assumed to be connected. We all think of it as, oh, the different math subjects, these are just different chapters in the same book. And it's our job to put the book in order, to discover the entire book, right? And this is the kind of thing, this kind of theorem is what has inspired a lot of solutions over the years. So one thing I've mentioned also is Fermat's last theorem, which was solved very recently, unsolved for hundreds of years. Yeah, hundreds. 300 years took to solve this. Andrew Wiles solved it in the mid-90s. Was a statement about expressions that look like this. How many ways, if n is assumed to be a positive integer, and a, b, and c, so it's either x, y, z, or a, b, and c, and a, b, and c are also assumed to be integers, how many solutions do you have to this equation? Will you always be able to find solutions, right? So for example, if I put a cube here, can you find positive integer solutions? If I put 7 here, can you find positive integer solutions? Now that was a problem in number theory. That was Fermat's last theorem. Fermat claimed that if your n was larger than 2, there is no solution. And that was a very strange thing to claim. He said he knew the proof. No one knew how he did the proof, but that's what he said. Right? This does not have any integer solutions if your n is larger than 2. And it was a problem in number theory. But Andrew Wiles discovered the solution to this problem by looking at a completely different area of math called elliptic curves. Which is a very specific kind of curve. It's like super specific in like analytic geometry. Like it had nothing to do with this particular kind of equation. Hey, what the pictures of these look like, it's not like that. It's not like, oh, if you graph this, you get this, something like that. No, the guys like this, they're cubic equations, right? What do they have to do with any power, right? But that's where he developed the solution to solve that. So there's this mixing and matching happening, and the kind of thought that inspires innovative ideas like that is a theorem like this. We can connect things that we don't think are connected. And that is a word to the wise. So whenever you feel like you're going through something and there's no reason for it, you're probably not being creative enough. A lot of people who go through college, oh, college education never helped me with anything. Well, it's kind of your fault. If you can't see a connection, you're not looking hard enough, right? Everything's connected. And in particular, finding errors and finding rates of change are connected specifically in this way. And there could be many other things that are connected in ways that we don't know. But because of the fundamental theorem of calculus, we know to look. At this point, I really should tell you about some properties of integrals, but I wouldn't get through all of them. Instead, what I'm going to do is I'm going to list some examples for you guys to try to suffer through over the weekend, and we can do them on Tuesday. We have Easter break starting on Thursday next week, I believe. So we have one less class next week. So let's try to get some work. I'm going to give you some examples for both part 1 and part 2. Oh, by the way, it turns out that those two statements I made, anyone can be part 1 or part 2. Turns out you can use the first one to prove the second one, and you can use the second one to prove the first one, and some people actually do it that way. I went from part 1 to part 2, so that's why I labeled it that way. And you know, when I was a little Javon kid growing up, you know, in the mean streets, that's always how I knew it. Part 1 and part 2 was this and that. But then after I became an adult, I realized that there are people who thought about the problem in the completely opposite way from me, and they prove this first and then do it that. And so when I'm telling them, oh, you use part 1, they're like, you mean part 2? No, I mean this. That's part 2. I'm like, no, that's part 1. I'm like, well, it really doesn't matter. So if you see it labeled in another way, it's not that one of us is lying to you. You can actually go in either direction, and there are proofs that go the other way as well. So you know, that funny thing is, there's another thing that threw me when I came here for college. Like my whole life, like when I was a kid in childhood, the equation of a line was y equals mx plus c. And I came here and I was like, oh, the equation of a line, you mean y equals mx plus b? And I'm like, what are you talking about? Why do you call it b? That's so weird. You're so weird. Yeah. Sometimes, you know, these little things, don't be driven crazy by that. It's easy to get crazy with it, you know, people using different notations. So, yeah. Part 1 and part 2 are interchangeable. People can come at this problem from many different angles. In fact, that is, again, a part of the inspiration of the theorem. Like you can get to the same answer through many different ways, and you never know when you're all doing the same thing. Let's do some examples on part 1 according to this class. Evaluate the following integrals. So I want you guys to actually take a shot at this, because I've told you theoretically how we can do it, but let's try to put that into practice. So this guy, we actually found the answer the long way using the series. I want you to do it according to the Fundamental Theorem of Calculus. Also try this one. Also try this one. Also try this one. Now the answer to this one is actually 0. That's going to spark some conversation. What do you mean it has 0 area? 0 area? 0 to the power of 3 of 3 over cosine squared x f 0 to 13 sine squared plus cosine squared. 1 to 4. Try those to test your knowledge on part 1. And you can try these to test your knowledge on part 2. Find the derivatives of the following. Only 4 examples here. Now, this is a topic that, to really get good at it, it's like you have to just drill a lot of problems. So you want to practice these examples, practice more, and after I go through these, find yet more examples and practice them. You'll be expected to get through things like this really quickly on a test in general. So you really want to overexpose yourself to these guys. Okay, so I have a function that's defined as an integral from 1 up to x, the sine of the square root. By the way, this function has no general antiderivative, so this is another reason how the theorem can help us. We can compute things that we couldn't compute before. So if you try to actually do this directly, by first finding the antiderivative and then differentiating that, you're not going to get the answer. B. That's up to 4. Zero to x cubed. We'll get through those next time and talk about properties of integers. For now, that's it. So a lot to think about, mathematically and philosophically. Go forth. I'll see you guys on Tuesday.